Module 1, Lecture B, Values and Expressions. By the end of this lecture, you will be able to use variables and assignment statements to represent engineering quantities clearly, apply arithmetic operators and built-in functions to compute engineering formulas, and format numeric and text output so calculation results are understandable. Variables and types. Variable basics. A variable is a named place in a program for storing a value. In engineering, variables help connect numbers like temperature, pressure, pipe length, or motor efficiency to the real-world quantities they represent. Clear variable names make code easier to understand, update, and share. Assigning a value to a variable means storing data under a clear name so the program can use it later. This connects a value, such as a measurement, with its meaning. Using variables helps programs avoid repeated raw numbers, reduce confusion, and make calculations more reliable. Variables let a program update values as it runs, making it adaptable when data or results change. In engineering, this supports tasks like changing simulation values or cost estimates as conditions shift. Each variable should have a clear purpose, helping beginners write programs that are accurate, readable, and easier to maintain. Python code. Variable basics. Variables give names to engineering values, and assignment links those names to specific measurements. Using clear names makes formulas easier to read and understand. The pipe is defined by two measured dimensions, a length of 12 meters and a diameter of 0.25 meters. These values describe its physical size and provide the basic inputs for later flow and material calculations. Set the water density to 997 kilograms per cubic meter and the flow speed to 1.8 meters per second. These values describe the water's mass per volume and how quickly it moves through the pipe, which are needed to calculate flow behavior. To find a pipe's cross-sectional area, use the area of a circle. Divide the diameter by 2 to get the radius. Square it, then multiply by pi. This area helps determine how much fluid can flow through the pipe. Volume flow rate is found by multiplying a pipe's cross-sectional area by the fluid speed. The result tells how much water passes through the pipe each second, measured in cubic meters per second. Mass flow rate is found by multiplying the volume flow rate by the density of water. This tells how many kilograms of water move through the pipe each second, which is important for engineering and design calculations. The pipe length is updated to 15 meters to match the revised design. This ensures later calculations use the new value and lets the program adapt without major code changes. The output presents key pipe flow results with clear labels and appropriate units. It reports the pipe length, diameter, cross-sectional area, volume flow rate, and mass flow rate, using consistent decimal formatting to make the values easy to read and interpret. The script summarizes water flow through a pipe by setting the pipe dimensions, water density, and flow speed. It calculates the pipe's cross-sectional area, then uses that to find the volume flow rate and mass flow rate. After changing the pipe length, it prints the updated length along with the diameter, area, and flow rates in a formatted output. Variable types. In Python, every stored value has a type that tells Python what kind of information it is and what operations make sense for it. In engineering work, common types include whole numbers for counts, decimals for measurements, text for labels or names, and Boolean values for true or false decisions. Understanding these types helps Python process data correctly and supports reliable calculations. Python's main numeric types are integers and floating point numbers. Integers represent exact whole number counts, while floating point numbers represent decimal measurements and are commonly used in engineering. Because floating point values are approximations, they are usually reliable but can cause issues with tiny differences or repeated calculations. Understanding the distinction helps prevent mistakes between counts, measurements, and rounded values. In Python, text and Boolean values help make data easier to understand, even in numerical work. Text can label information such as names or locations, while Booleans record true or false conditions, like whether a value is in range. Python can often infer a value's type, but choosing the right type helps both the program and the user understand what the data means. Python code, variable types. Variables store engineering information, and their types define what values they can hold and what operations can be performed. Using clear types helps make calculations easier to read and understand. An integer stores an exact whole number, such as assigning 8 to a bolt count. This is useful for discrete quantities where fractions do not make sense. Floating point numbers are used to store decimal engineering measurements, such as a beam's length in meters and its load per meter in kilonewtons. This allows values that are not whole numbers to be represented with the precision needed for accurate calculations. The component name, roof beam B2, and the force unit, kN newtons, are stored as text using a string function. This makes them easy to reuse later as clear labels in engineering calculations and documentation. Set the allowable load to 90 kilonewtons, representing the maximum safe load for the design. Then find the beam's total load by multiplying its length by the load per meter. This total force can be compared with the allowable load to check whether the design is safe. To check whether the beam design is acceptable, compare the total load with the allowable load. If the total load is less than or equal to the allowable limit, the design passes the safety check. Otherwise, it does not. The output checks each key value and its data type to confirm the program is handling information correctly. It verifies that the member name is text, the bolt count is an integer, and the beam length is a decimal value. It also displays the total load to one decimal place with its force unit, then reports whether the design passes as a true or false result. This script shows how common data types can manage engineering information. It stores values such as a bolt count, beam length, load per meter, descriptive text, and a pass or fail design check. It calculates the total load from the beam length and load per meter, then checks whether it stays within an allowable limit. When run, it displays each value with its data type to illustrate how engineering data can be stored, calculated, and verified. Meaningful variable names. Meaningful names make programs easier to understand, especially when values represent physical quantities. A clear name should show what the value is and how it relates to the problem, such as a real engineering measurement. Because code is often read many times after it is written, good naming helps teammates and your future self find errors and communicate technical ideas more clearly. Choose variable names that are clear but not overly long. They should show both what is being measured and its context, such as the kind of temperature or pressure involved. Because programming languages do not track units automatically, include units in names when needed to avoid mistakes. A consistent naming style makes code easier to read and helps prevent confusion. Meaningful names make code easier to understand, check, and maintain, especially in larger projects with many related quantities. Short or personal abbreviations may seem convenient, but they can confuse collaborators unless they are standard in the field. Descriptive names that reflect the physical meaning and context help reveal mistakes and make code serve both the computer and human readers. Python code, meaningful variable names. Use meaningful names to make engineering values easy to understand. Including units in names helps prevent calculation mistakes, and clear assignments show the physical context of the problem. The beam is defined as 4.5 meters long, with a center load of 1,200 newtons. The support spacing is set equal to the beam length, matching the setup where the supports are at the beam's ends. Including units in the descriptions helps keep the calculations clear and consistent. For a beam with a center load, each support reaction is half of the total load. The maximum bending moment occurs at the center and is found by multiplying the center load by the support spacing, then dividing by 4. This gives the key reaction forces and maximum moment needed to assess the beam. The output displays the key beam values with clear labels and units, the beam length in meters, the center load in newtons, and the left reaction force in newtons. Including units with each value keeps the results easy to interpret and preserves their physical meaning. The code reports the beam's maximum moment, an important result in structural analysis. It presents the calculated value with a clear label and the unit Newton meters, making the beam's critical load effect easy to understand. This script summarizes the main structural response of a simply supported beam with a central load. It calculates equal reaction forces at the two supports and the maximum bending moment at the beam's center. It then prints the beam length, applied load, support reaction, and maximum moment with clear labels and units, making the physical meaning easy to understand. Arithmetic operators help engineers turn measurements and assumptions into useful results. Basic operations, such as adding, subtracting, multiplying, dividing, using powers, and finding remainders can be combined to model real situations like total mass or average load. Choosing the right operator is important because it keeps the calculation aligned with the engineering problem. Order of operations determines how arithmetic expressions are evaluated. Powers are calculated before multiplication and division, and those come before addition and subtraction, unless grouping changes the order. In engineering formulas, using the wrong order can produce results that look reasonable but are physically wrong. Clear grouping makes the intended calculation easier to understand, check, and trust. In engineering arithmetic, operators must be chosen with the type of numbers and the meaning of the result in mind. Division may represent a ratio, rate, or unit conversion. Powers may describe area or volume, and remainders can show leftovers or complete batch counts. Thoughtful use of operators helps calculations match real-world systems, such as motion or energy use, and supports accurate problem solving. Python code, operator basics. Arithmetic operators let you write engineering formulas clearly, while parentheses show the intended order of calculation. Printing results with their units helps connect the computed numbers to their real-world meaning. We define the beam model using 3 key quantities: a total length of 6 meters, a uniform load of 850 newtons per meter, and 2 supports. These values describe the beam's size, the evenly distributed load, and the support points needed for later load distribution calculations. To find the support load, First, multiply the beam length by the uniform load to get the total force on the beam. Then divide that total force equally among the supports, so each support carries the same share of the load. A rod's radius is given as 0.012 meters. Its cross-sectional area is found using the area formula for a circle, pi times the radius squared. This area, measured in square meters, helps describe the rod's material properties and structural capacity. With 5 meters of stock and pieces of 1.2 meters each, floor division tells us how many complete pieces can be cut. It divides the total length by the piece length and keeps only the whole number result, so any leftover material is ignored. To find the leftover material after cutting full pieces from a stock length, use the modulo operation. It gives the remainder after dividing the total length by the piece length, which is the amount too short to make another full piece. Grouping determines how calculations are applied. If you add 200 to the total load but divide only the 200 by the number of supports, the average is incorrect. To get the correct average load per support, group the total load and 200 together, then divide the entire sum by the number of supports. The output presents key engineering results in clear units and rounded formats. Total load, load per support, rod cross-sectional area, number of full stock pieces, and leftover stock length. It also compares two average calculations, one with proper grouping and one without, to show how parentheses can change a formula's result. This script shows how basic arithmetic supports common engineering calculations. It finds a beam's total load and splits it between two supports, computes a rod's circular cross-sectional area, and uses division and remainders to manage cutting stock material. It also shows why parentheses matter by comparing average load calculations with different grouping, then prints each result with clear labels and units. Built-in functions. Python's built-in functions make engineering calculations faster by handling common tasks such as absolute values, rounding, and finding maximum or minimum values. They help engineers interpret measurements accurately and present results clearly, such as measuring temperature error or simplifying reported beam lengths and flow rates. Python's built-in functions make calculations clearer, shorter, and more reliable. They help engineers and analysts express tasks like finding a maximum load or minimum clearance directly, without repeating extra logic. This keeps attention on the engineering decision, rather than the mechanics of the computation. Built-in functions help turn raw engineering data into useful information for decision-making. They can summarize sensor or simulation results, such as finding peak vibration values or checking whether parts meet tolerances. Using these functions consistently also keeps complex calculations clearer, easier to verify, and easier to communicate. Python code, built-in functions. Built-in functions make common engineering calculations easier. In this example, they are used to summarize simple test measurements with results rounded for clear reporting. The test stores a target temperature of 80 degrees Celsius and a measured temperature of 76.8 degrees Celsius. These two values are used to calculate how far the actual temperature is from the desired temperature. Calculate the signed temperature error by subtracting the target temperature from the measured temperature. This shows both how far the measurement is from the target and whether it is above or below it. To measure the size of a temperature error, use the absolute value function. It turns a positive or negative error into a non-negative value, showing how far the measured temperature is from the target without considering whether it is above or below it. Beam load test results are stored as a list of load values in kilonewtons. This makes it easy to analyze the data by finding key values such as the maximum, minimum, and average load. To find the range of load test results, use the maximum function to identify the highest recorded load and the minimum function to identify the lowest. Together, these values show the extremes of the data and help assess the material's performance limits. To find the average beam load, add all the test results together and divide by how many results there are. In practice, this uses the sum function for the total and the length function for the count, giving the average load in kilonewtons. For engineering output, the temperature error magnitude and average load are rounded to 2 decimal places. This makes the results concise, readable, and easier to interpret in reports or summaries. The code prints a short summary of the main engineering results. It reports the rounded temperature error in degrees Celsius, then shows the maximum, minimum, and average test loads in kilonewtons with the average rounded for readability. Together, these values give a quick overview of the key measurements and calculations from the script. This script uses built-in Python functions to summarize engineering test data. It finds the temperature error and its absolute magnitude, then analyzes beam load results by identifying the highest and lowest loads and calculating the average. The rounded results are printed in a clear summary for engineering reporting. Built-in functions. Python's built-in functions help engineers handle common calculations quickly and reliably. They make it easier to find values such as maximums, minimums, absolute differences, and rounded results without getting lost in extra computational steps. This lets engineers focus more on the purpose and logic of their work while reducing errors. Built-in functions help express common engineering calculations clearly and efficiently. Absolute value is useful when only the size of an error matters, while maximum and minimum functions help identify important limits such as peaks or safety margins. Rounding functions make results easier to communicate when extra decimals are unnecessary. Using built-in functions well means thinking beyond getting a mathematically correct answer. Engineers must consider units, rounding, and realistic precision so results are not misleading. These functions support clearer, more disciplined calculations that are easier to check, explain, verify, and reuse in broader problem solving. Python code, built-in functions. Use the built-in engineering calculation tools to produce clear, concise results. Include measurements with appropriate engineering units and present outputs in a way that is easy to interpret. A short list is used to store 4 beam load measurements in kilonewtons. Keeping these values together makes it easier to perform later engineering calculations, such as identifying the highest or lowest load. 2 diameter measurements are stored in millimeters, the intended value of 50 and the actual measured value of 49.63. Comparing these values helps assess how closely the manufactured part matches the target size. Use the maximum function to find the highest recorded beam load in kilonewtons, giving the peak load experienced during testing. Use the minimum function to find the lowest recorded load. Together, these values show the range of loads applied to the beam. To find the manufacturing error in a diameter measurement, we take the absolute difference from the target diameter. This makes the error positive whether the part is too large or too small, giving a clear measurement in millimeters of how precise the process is. Round reported engineering values to appropriate decimal places for clarity and consistency. The peak load is rounded to 1 decimal place, while the diameter error is rounded to 2 decimal places, making both results easier to interpret and communicate. The output reports the key test results in a consistent format. The peak and lowest loads are shown to 1 decimal place in kilonewtons. The diameter error is shown to 2 decimal places, and the total number of tests is given from the number of load values. This script uses built-in Python functions to summarize engineering measurements. It finds the highest and lowest beam loads, rounds the peak load for readability, and calculates the rounded absolute error between a measured diameter and its target value. The output reports these results with units, along with the number of load measurements, making the results clear and easy to interpret. Readable output, print output. Print output in Python should do more than display numbers. In technical work, clear descriptive text helps explain what each result means, why it matters, and whether it is final or intermediate. This makes calculations easier to understand, test, explain, and trust, especially when they are repeated or reviewed later. When printing results, make the output meaningful to people, not just proof that the program ran. Raw numbers can be confusing, especially when several appear together. So label values such as pipe diameter or pressure drop clearly. Clear output helps others compare results, reproduce calculations, and spot problems during debugging. When producing print output, tailor it to the audience and purpose. During development, intermediate results can help check assumptions, but final output should emphasize only the key findings in clear language. Well-crafted output helps people understand results and make informed decisions, turning Python into a tool for technical communication, not just calculation. Python code, print output. Print statements are used to share the results of engineering calculations. Clear labels and units make numeric outputs easier to understand and interpret. We define 3 key beam properties for the analysis: a length of 3 meters, an applied load of 450 newtons, and a stiffness of 18,000 newtons per meter. Together, these values describe the beam's size, the force acting on it, and how much it resists bending. Beam deflection is estimated by dividing the applied load by the stiffness, giving the bend in meters. This value is converted to millimeters for easier comparison with engineering limits. It is then checked against the safety limit of 30 millimeters to decide whether the deflection is acceptable. The code displays the raw deflection value in millimeters, so it can be checked before adding labels or units for clearer presentation. The output presents 3 key beam values in readable units: length in meters to 1 decimal place, applied load in newtons as a whole number, and estimated deflection in millimeters to 2 decimal places. This formatting keeps the results clear, precise, and easy to compare with safety limits. The calculation checks whether the deflection stays within the allowed safety limit by comparing the deflection value in millimeters to the limit. It then displays the limit to 1 decimal place and reports whether the deflection is acceptable as true or false. The script estimates a beam's deflection under load by using the beam length, applied load, and material stiffness. It converts the result from meters to millimeters, prints the value with clear units, and compares it with a 30 millimeter safety limit. The final output gives the calculated deflection and states whether the beam meets the safety requirement. Formatted strings. Formatted strings help combine text with calculated results so output is easier to understand. In engineering and similar fields, numbers need clear context, such as what was calculated and why it matters. Presenting results in sentences turns raw data into useful communication for peers, supervisors, or clients. Formatted strings let you control how numbers appear, so results match the level of precision needed in each engineering context. They can make values easier to read by showing suitable decimals, tolerances, or currency formats. This keeps outputs consistent, reduces clutter, and supports clearer comparisons, summaries, and reports. Formatted strings connect numerical results to their practical meaning. They help present lab or design calculations clearly, such as whether a measured value or system performance meets expectations. Clear formatting reduces ambiguity, supports better decisions, and makes analytical programs communicate results more professionally and accurately. Python code, formatted strings. Formatted strings help make engineering results clear and readable. Including units and labels reduces confusion, while rounding values shows the level of precision that is practical for the result. The beam analysis begins by setting three key values: a beam length of 3 meters, an applied load of 750 newtons, and a stiffness of 28,000 newtons per meter. These inputs describe the beam's size, the force acting on it, and its resistance to bending, forming the basis for calculating deflection. The code estimates beam deflection by dividing the applied load by the beam stiffness. It then converts the result from meters to millimeters for a more practical engineering value, and also expresses the deflection as a percentage of the beam's total length to show how large the bending is relative to the beam size. The code first prints the raw deflection value in millimeters, so it can be compared with the formatted output. This shows the difference between plain raw data and a clearer presentation that includes context and precision. The output presents key beam analysis results in a clear, readable format. It shows the beam length in meters, the applied load in newtons, the estimated deflection in millimeters, and the deflection as a percentage of the beam length. Each value is rounded appropriately, so the results are precise and easy to interpret. Beam deflection is found by dividing the applied load by the stiffness, giving the bend in meters. For practical interpretation, this value is converted to millimeters by multiplying by 1,000. The same deflection can also be expressed as a percentage of the beam length by comparing the deflection in meters with the total length and multiplying by 100. This script estimates how much a beam bends under a given load. It uses the beam length, applied load, and material stiffness to calculate deflection, convert it to millimeters, and express it as a percentage of the beam length. The results are then displayed in a clear summary showing the load, beam length, estimated deflection, and deflection ratio. Unit labels. Unit labels give numbers clear meaning and prevent ambiguity. A value like 12 can refer to many different quantities, so labeling results with the correct units provides physical context and supports accuracy. In programming and engineering, clear output reduces misunderstandings when results are shared or used by software tools. When presenting technical results, always pair a clear label with a number and its unit. Units such as millimeters, watts, amperes, ohms, or volts connect the value to the physical quantity and prevent confusion with similar measurements. This is especially important when several results appear together, such as flow rate, pressure rise, shaft power, and efficiency in a pump report. Clear unit labels make results consistent, professional, and easy to trust. Choose a unit system, label values after conversions, and avoid mixing units without explanation. This helps prevent confusion and reduces the risk of serious errors in fields like aerospace and medication dosing. Python code. Unit labels. Unit labels make engineering results easier to read and help prevent interpretation mistakes. Formatting values clearly with their units makes output more understandable and reliable. The content defines 3 engineering quantities using clear descriptive names: beam deflection of 2.347 millimeters, flow rate of 18.6 liters per minute, and pressure rise of 245.2 kilopascals. These values describe beam bending, fluid movement, and pressure increase across a component. Descriptive naming makes the code easier to understand and helps prevent misinterpretation. The setup defines 3 key quantities for later calculations: efficiency as a fraction, shaft power in kilowatts, and heat transfer rate in watts. Clear descriptive names make the calculations and results easier to understand. Printing only the number 2.347 shows how unclear a value can be without units. In engineering, unit labels are essential because they give numbers the context needed for correct interpretation. The output presents key engineering results with clear units and controlled precision. Beam deflection is shown to 2 decimal places in millimeters, while flow rate and pressure rise are shown to 1 decimal place in liters per minute and kilopascals. This formatting makes the values precise, readable, and less ambiguous. To express efficiency as a percentage, multiply the decimal efficiency value by 100. This converts the fractional form into a percentage, making performance easier to understand and compare. The output presents 3 key results with appropriate formatting: shaft power in kilowatts to 2 decimal places, heat transfer rate in watts rounded to the nearest whole number, and pump efficiency as a percentage to 1 decimal place. This keeps the values clear, precise enough, and easy to read. This script shows why engineering results should be printed with clear unit labels. A number without context can be ambiguous, so the code presents values such as deflection, flow rate, pressure rise, power, and heat transfer with appropriate units and formatting. It also converts efficiency from a fraction to a percentage to make the result easier to read. The main message is that labeled, well-formatted output improves clarity and helps prevent mistakes. In this lecture, you learned to use variables and assignment statements to represent engineering quantities clearly, apply arithmetic operators and built-in functions to compute engineering formulas, and format numeric and text output so calculation results are understandable. In the next lecture, Lecture C, we will go over logic and flow. Thank you for your attention. See you all in the next lecture.